Alright guys, good afternoon. Do we have any questions before we start today's lecture? Alright, so now I have 34 students. So let me review what we did last time. So last time we discussed the concept of external forces, right? So I told you that external forces are vectors, okay? Vectors. And then you can write the vector in this way using one bar. So one bar means we are using one set of normal vectors. Depending on the direction of normal vectors must be determined by the choice of coordinate system. So if you use the Cartesian coordinate system fx, and then fx must be associated with unit normal in x direction. So make sure that here this fx and the magnitude of fx depends on the direction of x coordinate, okay? And then fy, ey plus fz and ez. And that depends, okay? That depends on the choice of coordinate system. Depending on the authors, some people, like me, like this initial rotation instead of using x, y, z. I'd like to use 1, 2, 3 instead of that. That would be better. And this is the nature of external forces. And what is internal forces? So internal forces are found in the interface of free body diagram, isn't it, right? And then here, please understand the nature of internal forces. So internal force, if I write N to represent normal internal force, then this is given by the integration of normal stress over the cross section, okay? And then the last time I emphasized you that stress to represent a stress state, so we need to use two different sets of normal vectors, the unit vectors, what I mean. So for example, so here if you want to represent a stress state, like which stretches a material like this, and then we say that this condition is a default positive. Okay, that's what we call it. This is a sign convention for the stress state. So if I represent this stress state using the normals like vectors for the external forces, here we have to use two bars, okay, which means here I have magnitude, and then first I have to say, okay, let's consider this is x coordinate, it's ex, and then also I need another bar for ex. What's the physical meaning of this two bar? The physical meaning of this two bar is one is representing the direction of the traction, of the traction. So here the traction means, you know, distributed force over the cross section, over this cross section. Okay, the force divided by this cross section area. That's the meaning of it. And what's the meaning of the second normal? The second normal represents the direction where we observe the traction. Okay, so okay, for example, so if I want to read the traction from the stress state, say if I want to read the traction from the stress state, then we have to use, you know, I have to read the projection of stress state, and in that direction, let's say this normal is what? Nothing but just Ex. Then what is it? Then this is sigma Ex and Ex dot Ex. Okay, the dot product between is equal to 1 because they are parallel to each other, identical in other words. By the way, I wonder if my YouTube is working well without any problem. Okay, so this is equal to 1, isn't it right? That's why we have sigma Ex1 Ex only. So that exactly representing this traction. Alright, what if we want to read that traction? Let me change the color. That traction. Then, okay, that traction is, how do you read the traction? The same stress state, and then I want to read, you know, the traction on this direction, isn't it? That this is equal to what? Minus Ex. Okay, so minus of, oh really, Sumini, let me check, is that so? You mean is there any problem in the resolution of the screen? How about other students? Actually, I cannot handle this because this is the problem of network. Maybe there are many professors who are giving lectures at the same time. And then the direction is what? Minus Ex. Maybe, okay. So it's not my problem, right? Actually, I'm giving this lecture, you know, exactly using the same computer so every time. Okay. Alright, so if you do that, this is equal to sigma 승재. 늘 유튜브 라이브 자체가 환경이 좋지 않아서 오늘 딜레이 매척에서 보는 게 okay. So sigma Ex and Ex, and then dot. So we move minus in front of this equation, Ex. Then that is cancelled because this is dot product is equal to 1. So it becomes minus sigma Ex. Okay, this is exactly that exactly represent this traction. Okay, please make sure that although in our textbook the textbooks calls the stress what I mean, there's no the textbook doesn't distinguish the stress from the traction, the internal traction, but they are different. Okay, the traction is the consequence of internal stress. So if you consider dot product, multiply or dot product in a certain direction where we observe the traction, then we can obtain the traction. Okay, so alright, so although I told you several times, what happened? So my iPhone has a problem. Wait a minute. So connection is missing now. 현민이, T means a distributed force. So when we define a free body diagram, so at the interface between two different bodies, then we must have internal traction. This is called traction. Is it okay for you? Any other questions? So we are talking about the internal force, right? So nature of internal force, to represent the internal force precisely by using stress. The internal force is integration of this stress, okay? So that's why to define the sign convention for the internal force, it must follow the sign convention of the normal stress. So which means if the internal force is for stretching a material, then this is positive. And then if internal force is for compressing the material, then its sign is minus, negative. This is a sign convention for the internal force. And then also last time that we discussed the sign convention for the stress, shear stress, isn't it, right? So here the shear stress is always acting as in pair form. So we have a shear stress component here and here, and to satisfy the momentum equilibrium, we need to have exactly same pair of the shear stress but in the vertical direction. But usually the normal stress is represented by conventionally sigma, and the shear stress is represented by tau. Okay. Is it clear? And then this is that was the definition of the shear strain. And then we discussed the concept of the shear modulus. The shear modulus is given by elastic modulus and the Poisson's ratio. Okay, which means shear modulus is not an independent parameter. It depends on the elastic modulus and the Poisson's ratio. In the case of linear homogeneous material. And then after the class in the last time, a student pointed out my mistake here. When we calculate the shear stress here, I made a mistake when I calculate the area. So the shear area is this. The thickness is multiplied by the perimeter of the circle. Okay, so last time I made a mistake. So here the shear stress is what? The shear force, and then divided by the shear area. Okay, so how do you calculate the shear force? So shear force means, okay, let's imagine an imaginary surface. Say I have a plate, and then we can imagine an imaginary surface here. And then here we need to consider the thickness. And then we must have some distributed force here, isn't it? We must have certain kind of distributed forces. Okay, so if you integrate all these distributed forces, then because of force equilibrium, its magnitude should be equal to applied force P. Simply speaking, the shear force is equal to applied force P is 110 kilonewton. And then now let's calculate the cross-section area. And this is equal to thickness times 창호 shear stress gamma's 단순히 각도값인가요? Yes, shear strain. Changho's question is about the definition of shear strain. So let me explain you about the shear strain after this, okay? After this example. And then this area is thickness times the perimeter. So pi times the diameter of the punch, isn't it? This is equal to thickness. How much is the thickness? 8 millimeters times pi, and then the diameter of the punch is equal to 20 millimeters. Okay, so now let's try to calculate the answer. If I want to use Newton unit for the force, then I have 110,000 Newton here, and then 160 pi in the denominator. Then this is the millimeter square. Then I would get the result, but its unit is what? Megapascal. So when we consider Newton in millimeter, then as the stress unit we have megapascal. Okay, so here let's go back to Changwo's question. And what Changwo's question is about this. Then how do we define the shear strain? Is shear strain is simply the angle change? Yes, you may understand in that way. This is a shear strain. Okay, so let's define the shear strain. So let's imagine that I have a body. So let's consider distortion. So if I have tangential behavior, then let's say by some reason my material body is deformed in this way, in the form of parallelogram. Then to measure this distortion, this is obviously shear, isn't it, right? So if you want to imagine a pair of folds which produce this kind of deformation, so we must have the shear stress here and here, okay? And then this distortion can be measured by this angle change, and this angle change is the shear strain. Let's imagine how we measure the normal strain. So normal strain, we measured normal strain in this way. Elongation divided by the original length, isn't it right? Similar to this. So what's the meaning of this elongation? It's a measure of deformation, isn't it, right? So here the shear strain similar to this. Say initial length, well, the length can be understood as initial dimension, okay? And then also some measure of deformation. Then how do you measure of deformation? This is the measure of deformation, delta, the delta. And then this is the original length, okay? So if you measure this shear deformation, delta divided by initial dimension L, then this is nothing but just angle change. Is it clear? Does it make sense? Actually, as given in your textbook, if you consider the shear stress and shear strain at the same time, it's very confusing. Okay, don't do that. Okay, so please consider separately. So here we are talking about the shear strain. Then please talk about the compatibility, the deformation, and then the strain. Okay. So when you talk about the internal force, external force, please consider force and stress separately, okay? Do not consider these two conditions at the same time. Don't do that. It's not a good habit. So once you have the information of strain, you toss this information of strain into the material law, like Hooke's law that we discussed last time. And then please calculate the stress value, and the stress is tossed to this force equilibrium condition to check the internal forces and then the relation between the internal forces and the external forces. Or you can do the other way, starting from the forces and stress, and then calculate strain, and then we check the displacement condition. Of course, for force side, we have to check the external forces, and also here we have to check the displacement boundary conditions. Alright, so now let's consider another example. Here we have shear inner strut. The first question is, please read these exam problems, okay? And then if I just summarize the problem itself, and then we have to consider a hollow member. And this hollow member is connected by a pin, here, by a pin, and to the gusset plate. And then the gusset plate is supported by 4 different anchors on the base. And then the question is, first, we have to calculate the bearing stress between the strut and the pin, okay? Which means we have to calculate the bearing stress here. So, let me draw the strut. and then we apply the force here, P, and then we have a hole, and then in this hole we have a pin, isn't it? And then because of the existence of the pin, we must have this traction here, traction vector, isn't it? So a force vector here. Okay, so now let's check the force equilibrium. For convenience, I want to consider this coordinate system. The sum of the force, sorry, not this direction. Sum of the force in this direction should be equal to 0. This is equilibrium, isn't it? So now I have a traction, the force per unit area, isn't it, right? So let's take only its magnitude. So T, because I'm choosing this direction is default positive. This is, according to our assumption, the T must have positive sign when we start this analysis. And then we need to consider this area, okay? The traction is force per unit area. That's why it's not a force yet. We need to multiply its acting area of the traction. And then here we want to calculate the bearing stress, isn't it, right? So instead of T, I want to use B, the bearing area. And then now let's consider this guy. Is it minus, plus? What do you think? What's the sign with respect to this coordinate system? Minus or plus? What do you think? What is the sign of the applied force P with respect to the choice of this coordinate system? Good. Should be minus, okay? Because its direction is opposite to default positive direction of this coordinate system, P. Okay? So we can calculate traction. Traction is equal to the magnitude of the external force P divided by the bearing area. Okay, now the question, the P is given. Where is the force P? P is 12 kilopounds. It's given here. And then how do you calculate the bearing area? The bearing area AB is here. This is the bearing area, isn't it, right? I have two of them. Two of the thickness of the strut. Thickness of the strut. And then I need to multiply the diameter of the hole. So the diameter of the pin is here. 0.75 inches times 0.75 inches. And what is the thickness of the strut? Thickness of the strut is, where is it actually? Thickness of the strut is gusset, thickness of gusset, base plate of 0.375. And then I can find it. Where is it? Wall thickness of the hollows here. Okay. This is 0.375 inches and then 0.75 inches square. So let's plug in here. And then here this T is the bearing stress value. So make sure that in our textbook the authors do not distinguish stress and traction. So make sure that bearing stress is a kind of traction, okay? The force per unit area. And the second question, the shear stress in the pin. Second question is shear stress in the pin. Alright, say, let's imagine if you look at the member from this direction. Then I have load P here. I have started, the P is applied, and then I have pin. Then on this side I can construct the free body diagram like this. Please imagine, to satisfy the force equilibrium, I must have a certain internal forces like this. So let's consider this is V and V. Let's apply the force equilibrium. Then simply 2V should be equal to applied force P. Okay? Then my shear force is P divided by 2. And then to calculate the shear stress, I need to calculate shear area. The V divided by a area of the pin. Isn't it? Right? So V is P over 2. And the area of the pin is pi over force times diameter of the pin. Where is it? Diameter of the pin is here. 0.75 square inches. So we can solve it one by one. And then the third question is the bearing stress between the pin and the gusset plate. This is also same. Then the force condition is same as before. We have force P, but we need to calculate the bearing area again. So here the diameter of the pin is the same, but instead of thickness of the strut, so we have to consider thickness of the gusset plate, thickness of this guy. Okay, the same. And then have a force question. We did the force force question is the bearing stress between the anchor bolt and the base plate. Bearing stress between the anchor bolt and the base plate. Alright, so let's imagine I have an anchor plate and then we have force in this direction. So first I have to calculate the horizontal component of the external force. This is what P horizontal is, P times cosine of 40 degrees. So if you want to use engineering calculator, first we have to convert the degree angles into radian angle. So pi is corresponding to 180 degrees, and then here we need to multiply 40 degrees. Okay, so once we have this, then let's look at the plan view. If you look at the plan view, we have 4 different anchors. We have anchors here. Sorry, in that direction. So I have PH. So the next step is I need to check the bearing area. So I have 4 of them. So 4 of them, and then I need to consider the bearing stress. Bearing stress, and then I have bearing area is equal to PH is cosine times pi 180 times 40. The remaining step is how do we calculate this bearing area? So bearing area is equal to the diameter of the bolt. Here the diameter of the bolt is given by 0.5 inches. And then the thickness of the anchor plate. Thickness of the anchor plate. Where is the thickness of the anchor plate? Anchor plate, the base plate, 0.375. 0.375 inches. Is it clear? And then finally we have to calculate the shear stress in the anchor bolt. Maybe I don't have to explain you that. It's the same as before. We need to, instead of this, put the same external force, but instead of the left hand side I have 4 of the cross-section area of the anchor. The shear stress tau, and then pi over force and diameter of the bolt square. is equal to external force, isn't it? Yeah, then we can calculate the shear stress. Alright, so next step is allowable stress concept. So allowable stress. So in 우리말 allowable stress is 허용 응력. And then allowable load must be called 허용 하중, isn't it? So here the allowable stress is the way of a way to define, how do I say, the way of define failure criterion. So let's imagine the stress strain behavior, stress and strain. Say if you imagine steel, then as the stress state of the steel reaches to yield strength value, and then it's gonna experience a horizontal plateau. So without increasing any stress state, the strain increases. Okay, hardening. So let's imagine what happened. Say I wanna build a cantilever structure. Say here I applied load P here. Or if I want to develop a column or hanger would be better. So apply load P. And then if you calculate the stress, then this is equal to P divided by the area. So if I apply force P here, I must have certain kind of elongation, isn't it? Now how do you calculate the elongation? Elongation is strain times initial length. If the deformation is not what I mean, as long as we consider small deformation problem. But okay. So if you consider small load and my stress is small compared to the yield strength value, and then I have a unique strain value here. So if I apply the small load, then I have small deformation, isn't it? So as the final user of the structure, because I can calculate or I can imagine the level of deformation, it would be okay. But if my stress value is closest to the yield strength, then I have relatively large strain. Then if you imagine the nature of external load, there is a fluctuation. Now also there is a fluctuation in the quality of the material too. So in the worst case, maybe the stress caused by the external load may exceed the material capacity. Then what happens? So if I increase the load, beyond of the yield strength value, then my strain suddenly increase to up to this point by this functional relation, isn't it? My structure suddenly undergoes significant amount of deformation because of this plastic deformation. So nobody wants that situation, isn't it? So that's why in actual design procedure we limit the stress value up to certain level, and this stress value is much smaller than the yield strength value. That's why yield strength is very important. The stress level that we allow, the stress level we allow is smaller than the yield strength value. That's the meaning of allowable stress. So if you divide the actual strength by the required strength, for example, here if I want yield strength as the actual strength and then allowable stress value, then we can obtain the factor of safety or the safety factor. To avoid a failure, the factor of safety must be always greater than 1. And then here the safety margin. 안전 margin. Okay. The factor of safety is called in 우리말 안전율. Okay. 안전율. The safety margin is factor of safety minus 1. This is the definition of the safety margin. And this is what I explain you. And then because we are using the linear elasticity, we can apply the same logic to the force level too. Okay, this is an example of allowable stress of allowable load. So first we have to calculate the allowable load based on the hanger's material properties. For example, let's say the yield strength of a hanger is given by Fy. And then to calculate allowable stress, we need to divide this yield strength by the safety factor n, isn't it right? Then we can obtain allowable stress. Now how do you calculate allowable load? Allowable load is equal to allowable stress times the cross-section area of this member. Is it clear? Okay. Now here is the comment for the design procedure. What is the design procedure? The design procedure is to determine structural properties in order for the structure to support given load and perform its intended function. If material is given, then we need to determine the cross-section area of the member. Now here we did. So look at this. Say I have external load. To guarantee the safety, my external load should be less than my allowable load. Now how do you calculate this allowable load? My allowable load is safety factor times allowable strength times the cross-section area, isn't it? Okay? And then to satisfy this inequality, then I can determine the cross-section area of the member. Alright, and here is a summary. So we discussed different definition of stress components, normal stress and the shear stress and the normal strain and shear strain. And then we also discussed the Hooke's law too. And then this is a definition of the Poisson's ratio. And then this is a definition of bearing stress. And we did some of examples. Here, let me finish this chapter before we move to chapter 2. So let me take 10 minutes break. So here the time is 4:08 and then we'll resume the class at 4:18. By the way, you have homework here, okay? This is your homework problems. 주승이, I will ask my TA. Do you have any questions? We just finished the introduction. 현민이 actual strength를 정확하게 몰라서 actual strength 자리에 왜 항복응례들? 현민이, you can define any strength, any value as the actual strength. What's the reason that we choose the yield strength as the actual strength? Because we want to use the linear elasticity. So once the stress reaches to the yield strength level, then the stress-strain relation ceases to be linear elastic anymore. That's why we usually choose the yield strength value as the actual strength. So you are right. You can choose ultimate strength as the actual strength, okay? Depending on applications. For example, if you consider high strength anchor, then the yield strength value is not that clear because there is no clear kink point where the stress strain curve becomes horizontal. There is no such place. In that case, they use the ultimate strength value as actual strength. Alright, so now let's move to chapter 2. The subject of chapter 2 is actually loaded members. Alright, so here what we want to do is we want to study the changes in lengths of actual loaded members based on the force displacement relation. And then also we'd like to study the concept of statically indeterminate structures. And then we'd like to discuss how to consider the effect of temperature or misfit, non-mechanical deformation. And then here we'd like to talk about the concept of normal and shear stresses on inclined cross-section at a point in the actual loaded members. Okay, and also we can consider some these aspects, and that include stress concentration, the how stress increases by a local problem, and then as the last item, so we want to discuss strain energy, and then how we handle the fatigue stops as just information. But we're not gonna discuss the concept of fatigue or nonlinear behavior in this undergraduate course, especially at least in this classroom. We wouldn't do that. So first, let's consider spring, the coiled spring. So if you imagine a coiled spring, okay. So let's imagine we apply load to a spring, and then here I'd like to consider a spring. Usually we can idealize spring in this way. These are spring elements, and then we apply a pair of load to both ends, let's say P and P. Then as the consequence of this loading, we have certain elongation, isn't it right? We must have elongation. So let's say delta. And then we can plot the load P and the elongation in a two-dimensional graph. So we applied those small load P, P1, and the P2, and the P3, and then we measure the corresponding elongation and 2, and the elongation 3, blah blah blah. Okay, so we may have multiple points, isn't it? So if you connect all these points, then we can obtain this linear behavior, and the slope of this linear curve is called spring modulus. 이는 우리말 스프링 계수. So of course, if you apply load beyond, the ultimate or yield load of the spring, then it shows nonlinear behavior. So let's limit our attention only up to the proportional limit. So if the load is smaller than this proportional limit, then our response, the response of spring, is linear elastic. Okay, and here the K is spring modulus, or as given in our textbook, it is called stiffness. In 우리말 강성, stiffness. And then the flexibility in 우리말 유연도 is defined as 1 over the stiffness. This is flexibility. The physical meaning of stiffness is this: when you apply the unit displacement or unit deformation, then the force caused by the unit deformation is defined as stiffness. And the flexibility, when you apply the unit force, then we can the corresponding deformation is defined as flexibility. Alright, so first I wanna in this section, so we wanna consider prismatic bars. The prismatic bars means there's no change in the cross section between two reference points. Let's say we wanna consider point 1 and point 2, and that the point 1 and point 2 is connected by a member. And then here we'd like to assume the shape of the member is constant over this cross section. Okay, that's the meaning of prismatic bars. So we may consider different shapes of the section, like circular section or rectangular section or hollow section or I-shaped section or channel section, blah blah blah. Okay, alright, so let's consider analysis procedure. Okay, so now I have a bar. One side is supported. Okay, and its length is given by L. This is dimension. And then its cross section is measured by A. This is cross section area. And of course, we have to provide the material properties to the elastic modulus. And then it is subjected to the external load P. Alright, this is the condition of the problem. And then because I have a force, and then there must be a reaction here, reaction R. And then I want to denote here is point 1 and point 2. Alright, now before we start our analysis, the very first step that we have to do is we have to introduce a coordinate system. So what kind of coordinate system that we want to use? You want to use this coordinate system. This is option 1. And then if you don't like this, we can consider this coordinate system. This is option 2. So what do you want? What kind of option that you want to use for the choice of coordinate system? Now, what coordinate system that you want to use? Option 1 or option 2? Alright, so you want to use option 1. So please make sure that this is a vector problem, okay? So I have for external load P, this is a vector. So what kind, whatever your choice for the coordinate system is, you must have the same result, okay? So I want to choose option 1 according to your choice. All right, so let's choose this one. Okay, so once you choose this, then we can apply the force equilibrium. Let's say I want to start from here, the force equilibrium and stress, and then stress and strain, and then the displacement and strain. That's what you want to do. But let's choose this path for our analysis. Alright. So first, we have to consider the force equilibrium. The sum of all the forces in this direction, okay, should be equal to 0. And then I have reaction R. So please make sure that the direction, so we assume the direction is in the right hand direction. So according to the choice of my coordinate system, its sign should be equal to positive, isn't it? So right hand direction is positive. And then plus P is equal to 0. So can you calculate the reaction? Yes, we can calculate the reaction. The reaction is equal to minus P. Okay, so we just consider the relation between the external force, internal force, and the reaction. So we were able to determine the reaction from the external force. And the next step is I need to identify the relation between the stress and the force. Okay, so here we want to consider small free body diagram. So let's consider the free body diagram here. So if you consider the free body diagram, I have this free body, and then I have the external force P. And then to satisfy the force equilibrium, I must have some traction, isn't it? I must have some traction. So we can consider traction in this direction. Let's say this is option 1. And then my traction should look like this, caused by the stress. Option 2 as the stress value. What is correct? Option 1 or option 2? Option 1 or option 2? 현민이 option 2. And how about other students? 수민이 option 1. That option 2. Okay, 수민이, why do you think it must be option 1? Actually, the answer is option 2 actually. Well, 수민이, why do you think the option 1 would be the correct choice? The saying again, so in our textbook, there is no distinction between the stress and traction. But please make sure that here we are representing a stress state, okay? Stress state. That's why we need to consider the sign convention for the stress. The default positive is what? A state where the material is stretched. If you look at this, it compresses the material, isn't it? So this is compressive stress state, and this is tensile stress state. That's why we have to choose this. Okay, so once you choose this, I'm ready to calculate its magnitude. Okay, so now let's consider for this local system, I want to consider everything in the right hand direction is positive. To satisfy the force equilibrium, this guy should be equal to 0. So this is equal to So it's heading the left-hand direction, right? So according to the sign convention of this, that should be minus of sigma and the cross-section area. Alright? And then plus P. So can you calculate the traction? The stress is equal to P over A. Isn't it right? 수민이, this is, 수민이를 생각했습니다. But you note 1. Alright. Here we just calculate the stress value. So because now I have stress, we have to calculate the corresponding strain value. So make sure that stress and strain, this is a material law. So material law means it is applied to each material point, alright? Each material point. So strain by Hooke's law is given by stress divided by elastic modulus. Okay, so let's plug in here. This is equal to elastic modulus and cross-section area and then load P. Alright? Then what's the next step? Now we are here. The next step is we need to determine the displacement. Okay? Alright, so now let's check the displacement. So please make sure that definition of strain. Definition of strain is elongation divided by the length, isn't it? Okay, so let's consider here. So I have support and then I have bar here, 1 and 2. So how do you calculate the elongation? We can measure the displacement at node 1 and also we can measure displacement at node 2. How? In this direction, because we are using vector. So if you want to deal with vector component, how do you measure this elongation? So make sure that this is my coordinate system, okay? Elongation is, the first choice is what? U1 minus U2. The second choice is U2 minus U1. What is the correct choice for the calculation of elongation? Option 1 or option 2? How do you calculate the elongation? Which one is correct? So again, elongation is different from displacement. Displacement is a vector. The elongation is measure of the difference of displacement in certain direction. This is elongation. Because our coordinate system is this, that's why we need to subtract u1 from u2. Okay, that's how we calculate elongation. Alright, so let's look at this. So here I have a strain. Strain is equal to the elongation divided by the length. This is given by load P divided by elastic modulus of area. And then let's look at this equation carefully. Instead of elongation, we need to consider u2 minus u1 and divided by original length is equal to P over EA. And then now let's consider the boundary condition. Because node 1 is supported, u1 is equal to 0, isn't it? Because of boundary condition. That's why we can calculate the displacement u2 very easily. This is equal to L over EA and then apply load P. According to our definition, and this is called flexibility. Okay? Or we can write in this way. P is equal to EA over L the U2. Now how do you call this? This is stiffness. Okay? Any questions? So let's try to solve the same problem with different choice of my coordinate system. Okay, so I have exactly same problem. I have bar, and the end of bar is subjected to load P in the right hand direction, and then I can imagine a reaction here. So not like before, so we want to choose this coordinate system. This is the default positive direction. Okay, so now let's choose the force equilibrium. Alright, and then I want to choose, this is positive. Sum of all the forces should be equal to 0. Then this is equal to minus R and then minus P is equal to 0. So again, the magnitude of reaction is determined by minus P. Okay, the same conclusion. So now let's try to calculate the stress. So let's consider the free body diagram here. Then I told you several times that the sign convention for the stress is different from the sign convention for the force component. So we have determined the sign convention from the point of view that whether the the stress stage stretches the material or not. So we want to consider this as default positive. Okay, sigma. So let's consider the free body diagram. So if you consider the free body diagram for this, then I have stress and load P, and we can determine the stress value very easily. So P divided by the area. Okay, same. And then we can determine the strain by using the material law. So I'm following the procedure that I explained you a long time ago. The strain is given by stress divided by elastic modulus. This is P over EA. So once you did this, then we need to move to the place of compatibility. The elongation is given by, here we have to be careful because this is my choice of coordinate system. So how do you calculate the elongation? So in this case, elongation is what? Elongation is, sorry about it. The elongation is delta is U1 minus U2. This is elongation, okay? So because of choice of coordinate system, not U2 minus U1. Okay? So now let's consider here. Then now because of boundary condition, U1 is equal to 0. Alright, so my elongation is from the strain times the original length. This is equal to L over EA times applied load P. Okay, let them equal to each other. So U2 is equal to minus L over EAP. So look at this. So when you choose the coordinate system, the last coordinate system, we had U2 is positive L over EAP. But in this time, I have U2 is what? Minus L over EAP. Why we have minus sign here? The reason is because I'm choosing this coordinate system. What's the meaning of minus displacement? Minus displacement means, this point is moving to the right hand direction. That's the meaning of minus. If you look at the physical meaning of the solution, so it doesn't matter the choice of the coordinate system, we always have the same conclusion. Is it clear? Okay, so let's solve the same problem in another way. Say I want to solve the same problem another way. So I have load P and I have a reaction. Okay, so in this time I want to start my analysis from the displacement, and then I want to calculate the strain. Once you have strain, I want to calculate the stress, and then I want to check the force condition. That's what I want to do. Okay, so first I have to identify the nodal position 1 and 2. Alright, so now let's check the compatibility condition first. So if you check the compatibility, I can calculate the elongation by U2 by U1, isn't it? But because of the boundary condition, U1 is equal to 0. That's why this is equal to U2. Are you ready to calculate the strain? This is a displacement. Now I can calculate the strain. The strain is defined as elongation divided by original length. This is U2 divided by the length L. Now what's the next step? Next step, I want to use the material law. Or in this chapter, we are using Hooke's law, isn't it, right? So if you use Hooke's law, stress is given by elastic modulus times the strain. And so it's very easy, you know. It's easy as 1, 2, 3. Just plug in the strain values here. The elastic modulus times elastic modulus divided by the length L and U2. Isn't it so easy, right? Okay, so I was able to calculate the stress just before. What's the next step? Next step is force equilibrium. So let's consider a free body diagram. This small free body diagram. And then we can imagine the stress in this way, because this is default positive, isn't it? So if you check the force equilibrium for this, and then the stress times the cross-section area is equal to P. Look at this, okay? You can check the magnitude very easily. Then let's plug stress here. Then elastic modulus times area and divided by length L, U2 is equal to P. So U2 is equal to L over EA times P. Exactly same conclusion, isn't it? Do you have any questions? Okay, so here I have a slide for cables. So in the case of cable, the cable, a cable cross section consists of many wires. Okay, so usually the wires are twisted to form a cable cross section, and then as you see, cable is twisted, and then it would undergo more deformation. That's why the flexibility of cable is greater than solid material. That's why in the case of cable, instead of using the modulus for the solid material, we have to use effective modulus for cable. In 우리말 유효 개수, 유효 탄성 개수, okay? 유효 강성 of the cable. So let's consider a simple example here. So I have a rigid L-shaped bar, and then I apply load here, and then the bar, the L-shaped frame. So I have an L-shaped frame, and then I have a hinge here. Then the hinge is supported by this spring. Okay, and then we apply load W. Now first we have to calculate the end displacement at this point. Okay, this is point A and point B and point C. and then the length is given by B, and then this is given by C. Alright, so first this is hinge. The hinge means hinge cannot resist any rotation. That's why I want to check right away. Because this is spring, in point C, because of spring, I must have this force here. Okay, so let's check the moment equilibrium. So moment equilibrium with respect to point B is equal to 0. If you want to talk about equilibrium. So moment produced caused by the load here is what? The force times arm length is equal to B. And then if you consider this direction is default positive, then this force, let's say I want to call this F, then that produce minus moment, the F times C. So I can calculate the force F, acting on this spring. F is equal to B over C W. Okay, so now next step, let's try to calculate this elongation. The elongation is equal to what? Elongation is equal to spring modulus times 1 over spring modulus times the applied force F. This is B over C and the weight W. So all the information is given. The stiffness and applied the magnitude of the force and the dimension of B and C. So once we calculate this elongation, then we can calculate the amount of adjustment. The pitch, elongation divided by pitch is the thread. Okay, so next subject is bars with intermediate axial load. So far we considered only one load, isn't it? The next subject is multiple load. Okay, here we just calculate how to calculate the elongation of a bar. So if you have a one-dimensional bar, look at this. So if I have a one-dimensional bar, so we were able to calculate the displacement, isn't it right? Solution of one-dimensional bar. One-dimensional bar. Sorry. So one-dimensional bar is what? The elongation. The elongation is proportional to the internal force. Okay? And how? We can calculate the elongation by using L over elastic modulus times area and then internal force at that point. Or in another way, the internal force is what? Elastic modulus times the length and the elongation. Okay, so let's use this formula. Let's look at this example. I have a hanger, and then I have bar. So I want to call this as point A, and then this is point B, and then point C, and point D. Then we have three different loads, PB, and then PC, and the PD. Their lengths are given by L1 and L2 and L3. Alright, but how do you calculate the overall elongation? The overall elongation is elongation of segment 1 plus elongation of segment 2 plus elongation of segment 3. So I'm following the procedure given in our textbook. Okay, then how do you calculate the elongation of the first segment? This is the first segment. Well, I mean, let's change different color. This is the first segment. This is, okay, this is flexibility. L1 divided by elastic modulus of 1 and the cross-section area of 1 times internal force of segment 1. In the case of segment 1, I have internal force N1 and N1. How about segment 2? Segment 2, delta 2 is equal to L2, E2, A2, and N2. So every calculation is systematic. Delta 3 is L3, E3, A3, and N3. Okay? Okay, so let's consider one by one. And then I want to consider reaction in this way. Okay, so let's consider first, let's consider the free body diagram. I want to consider the free body diagram. This is free body diagram 1. And then this is second free body diagram. And this is a third free body diagram. And this is a fourth free body diagram. Okay, let's start from this. Okay. If you start from the last one, let's consider omega 4. Then if you consider this, the point D is subjected to the external load PD. And then we need to consider, the internal force N3. So make sure that I told you several times that, the nature of internal force is same as the stress. If it stretches the material, it's a default positive. So if you don't know magnitude, what I mean, if you determine the internal force, first you have to assume, the condition is default positive. So here I want to consider this direction because that stretches this material segment, okay? So according to this, if you consider force equilibrium for this body, I can determine N3 is very easily. N3 is equal to PT. Isn't it, right? So let's move to omega 3. Let's move to omega 3. This is omega 3. I have point C. It contains point C. At point C, I have external load PC. And then there is internal force N3, and also we need to consider internal force N2. So make sure that the both internal forces stretches the material. Then if you consider free body diagram or force equilibrium, sum of force in the all the vertical direction is equal to 0. Then I can calculate the force I can check the force equilibrium condition. N2 minus PC minus N3 is equal to 0. So here N2 is equal to PC plus N3. The N3 is given by PD. We just calculate N3 value. This is equal to PC plus PD. Isn't it? It's so easy, right? So I can move the next point, omega 2 and omega 1, to determine all the internal forces. Okay? This is the approach that we can take from the procedure given in textbook. Let me choose another way. We can use this diagram. So I have force and strain, force and stress, and displacement strain, and stress and strain. That's what I want to use. And I want to start from displacement. And I want to calculate the strain and the stress and display the forces. That's what I want to do. Okay, so first I have to idealize the structural system. and then I have point A, B, C, and D. I have PD, and then PC, and PB. And the dimensions are given in this way, L1 and L2 and L3. Alright, first we have to introduce our coordinate system. So we have to introduce our coordinate system. This is my default coordinate system, okay? And then if we do that, and this is my x coordinate system. And now I want to choose, this is horizontal axis as the displacement u, displacement component. And then make sure that point A is fixed. The displacement here should be equal to 0, isn't it right? And then at point B, we have arbitrary displacement, UB. This is equal to UB. Is it clear? And then at point C also, we must have arbitrary displacement, UC. And then UD. Is it clear? And then this is the profile of displacement, depending on our choice of nodal displacement. Alright, we are here. We assume the distribution of displacement field. The next step is we need to calculate the strain field, right? How do you calculate the strain? The strain is elongation divided by the length. Strain of AB segment, strain of 1 is equal to elongation UB minus UA. UA is equal to 0. That's why UB divided by L1, isn't it? And then strain of 2, this is equal to elongation is what? UC minus UB. UC minus UB. Make sure that when I calculate, when I check the displacement field and the corresponding strain, I never discuss any internal forces and external forces, never, okay? I consider only displacement, deformation, okay? Doesn't matter how the deformation was caused, okay? I don't care about it. I consider only the displacement field, only deformation and the corresponding strain divided by L2. And then epsilon 3, strain in third segment is also same. UD minus UC and L3. Okay, this is a calculation of strain. Now what's the next step? Because we just strain, the next step is stress, calculation of stress. The sigma 1 is what? The elastic modulus times strain 1. This is equal to L1 E1 UB. And how about stress of second segment is equal to E2 epsilon 2. This is equal to what? L2 E2 UC minus UB. Sigma 3 is equal to E3 epsilon 3 is equal to L3 and E3 UT minus UC. Okay? It's so easy, right? So easy. So we finish it up to here. Now what's the next step? We have to check the force equilibrium. So we do one by one, okay? Let's consider the free body diagram here. Okay, let's check the free body diagram. And I have PD. And then this is my sigma 3. So, from the force equilibrium, so PD is equal to sigma 3 times area, cross-section area. This is equal to what? E3 times A3 and L3 UD minus UC. Is it clear? Okay. But according to this, I have one equation and two unknowns. That's the problem. So that's why we have to move to the next point. The next point is here, isn't it? This is the next point. At the next point, we have load PC. The load PC. And then this is my sigma 3 and the sigma 2. Again, I want to choose the force equilibrium conditions. If you choose the force equilibrium condition, sigma 2 A2 minus sigma 3 A3 minus PC is equal to 0. So let's plug the condition for the stress. Sigma 2 and sigma 3 is here. Okay? And also we check the force equilibrium here and also here. Then we can solve finally. We can formulate everything in terms of nodal displacement. Then we can solve for the nodal displacement. This is a more general approach to handle, this complicated problem. Do you have any questions? Here I'd like to take another 10 minutes break. Ooh. Do you have any questions? 현민이 일론게이션 일반식에서 앞에서는 n 대신 외력이 사용됐는데 정의상 n이 맞고 앞에서 그렇지 현민이 you're right. The counterpart of the elongation is internal force. Yes, you are right. Simply we use the P because its value was equal to the internal force. Actually, the textbook is rather confusing, So I don't like the way of this textbook. But this textbook is really, Bible. This textbook is used in most of universities all over the world. Okay? So although I know something wrong in the description of the textbook, but it is not that easy to change the system. But instead, I'm explaining, right? So please pay attention to the difference between the elongation and displacement, and also internal force and the external force. Good question. I will give you credit. Other questions? Okay, although we still have the break, but let's resume to class a little bit earlier than the time. Alright, so let's consider if we have to consider bars consisting of different cross sections. Okay, here I already in this example I already covered when we have different cross sections. Okay, so this approach can be applied to any types of cross section. Okay, that's why I don't want to repeat. 동현이 홍동현 why we choose PB is upward. Well, it is given, it is given in the textbook. I don't have any reason. Yeah, it depends on the way of the way of the loading condition. Sometimes we have to consider load upward, sometimes downward. It depends on the load, okay? Okay, so here actually this diagram is rather confusing. Okay, don't do that. So you'd better use this diagram. So we'd better use displacement. Okay, the displacement is better. Or if you can use this diagram, provided that you understand the characteristics of diagram. This is elongation and this is internal forces. Okay, please keep in mind the internal forces are different from the external forces in this nature. The external forces are vector, okay, vectors, but internal forces are integration of resultant integration of stress state. So although we can represent the internal forces using we can check the internal forces using the force equilibrium. So the nature is different. Okay, and then this is how we extend the approach for continuously changing cross sections. Even for the continuously changing cross sections, we can integrate. We can calculate total elongation by integrating the individual elongation for the small segment. Okay, so according to the formula, this is the flexibility dx, the length divided by elastic modulus and cross-section area, and times the applied force, isn't it? So if you have distribution of internal force, then using this integration I can calculate the total amount of elongation. And this is how we derive the governing equation for this problem. Please refer to this derivation for your reference. So let me skip it. So I prepared this lecture note only for your reference. So I'd like to skip it. Alright, so here I explained you already. So maybe I can skip it. And also this. So now the next subject is statically indeterminate structures. Statically determinate structures versus statically indeterminate structures. Okay, so statically indeterminate structures means in first case we can determine the reaction. We can determine the reactions only by using the false equilibrium. Then we call it statically indeterminate structures. What I mean in my diagram, the force and stress and strain, displacement strain. In the case of statically determinate structures, so we don't need other conditions. We need only this condition to determine all the forces, including the reactions and the stress condition. Okay? So if you finish our analysis by using the force equilibrium, or if you can determine the stress by using only force equilibrium, so we can call my structure system statically determinate structures. Is it clear? 고수민 10 to 14까지는 공부 안 해도 돼. Yes, you have to. 수민아, 해야 돼. But I already explained you all of this. Okay? I already used this approach to the same example problem. Please look at my lecture note. That's why I don't explain you that. So maybe the ADD stands for what's ADD? ADD stands for, you know, the actual displacement diagram. So where is the ADD? This is my ADD. Is it clear? This is ADD. So once you calculate the nodal displacement, then we can plot ADD naturally. Is it clear? Okay? Now look at this. This is my strain. So if you calculate all this strain, then I can calculate the strain. I can draw the distribution of strain. Okay, so because you asked me that question, so next time I will show you how we can do. Okay? And in the case of statically indeterminate structures, we have to use all of these three conditions to finish our analysis. That is the statically indeterminate structures. In 우리말, this guy is called 정정구조물. In 우리말, it is called 부정정구조물. 부정정구조물. Actually, in the sense of analysis, what I mean, actually in our textbook, in many classical education, 부정정 구조물 is much different from 정정 구조물. But if you understand this relation, okay, there's no special difference between statically determinate structures, statically indeterminate structures. Okay, so let's try to tackle this problem. Okay, so let's consider this. Let's consider this problem. So first we have to identify, or we have to simplify the structure. Say I have one support, and then I have two different bars. And then here point A, and then I want to call this point B, and then let's say I want to call this point C. Then we have one concentrated load P, downward load. So let's say the P is positive number. And then I need to introduce a coordinate system, isn't it right? So I want to consider this is my default positive direction. Because this is default positive direction, I'd like to assume this reaction at point B, it's RB, and then RA. Okay, so let's check the force equilibrium to determine the reaction. So if you check the force equilibrium, what I mean, I'm doing this force equilibrium, okay? The sum of force should be equal to 0. So if you count all the forces, RB and P and RA in this system. So RB, obviously this is positive because its direction is same as the default positive direction of my coordinate system. And also this guy too, RA. And then this is minus, right? P is equal to 0. Is it clear, right? I have one equation, two unknowns, okay? One equation and two unknowns. So we cannot determine the reactions. So there are many sets of the reactions which is satisfy this force equilibrium. That's why we cannot finish our analysis by using the force equilibrium condition alone. We cannot do that, okay? So we have to go one by one. Okay, let's consider the free body diagram for this. If you consider free body diagram, I have reaction RB, and then I have stress component sigma BC, isn't it? So if you look at the force equilibrium for this, sigma BC, and then the area of BC segment plus RB is equal to 0. Is it clear? And then here I can calculate sigma BA. Sigma BA is equal to minus of RB and then A, area of BC segment. This is how I calculate the magnitude of stress. Oh, sorry, B, not BA, BC. Sorry about it, BC. Okay, so now let's consider the free body diagram for this. If you consider that free body diagram, then I have force P. And then this is my default positive, isn't it, right? This is sigma BC. And then this is sigma AC. Again, sigma AC times area of AC segment minus sigma BC times area of BC segment, so minus P is equal to 0. Okay, so let's plug sigma BC here. The sigma AC times area of AC is equal to, we have sigma BC, so P minus RB ABC and then ABC cancels. Okay, so this means sigma AC is equal to what? P minus RB divided by area of AC segment. This is the calculation of sigma AC segment. Okay, so now let's consider this free body diagram. If you consider that free body diagram, we have RA, and then we have sigma AC. Okay, so RA minus sigma AC of area of AC is equal to 0. Let's plug in sigma AC here. Then RA minus AAC P minus RB times AC is equal to 0. So it cancels. That's why finally I have RA plus RB is equal to P. Okay? This is my force equilibrium. And then what's the next step? Next step is we need to calculate elongation. We need to determine the strain value. Strain is, we can determine the strain by this constitutive equation. We determine the strain epsilon BC segment is elastic modulus times BC segment and the stress of BC segment. This is minus EBC and the ABC and the RB. Okay? And also we can determine the strain of AC segment. AC segment is equal to EAC, the AAC, P times RB. Isn't it? And what's the next step? We need to check the displacement. Epsilon BC is calculated by what? I have BC. This is UC minus UB divided by the length of BC. UC minus UB is equal to 0, and then the length of BC. Isn't it? And blah blah blah. And this procedure is very complicated. That's why I choose another approach. I want to start from my analysis from here. First, I want to plot the displacement field, and I want to calculate the strain, and then stress, and then force. That's what I want to do. Okay. So A, B, and point C, I have a load P. Okay, and then this is my coordinate system. And then I can plot my displacement. This is my x coordinate. And then make sure that point B is fixed. And point A is also fixed. UA and UB is equal to 0. So only non-zero displacement, only non-zero nodal displacement UC among A, B, and C. So I must have UC. Isn't it? But according to the loading direction, I must have displacement downward, isn't it? So which means according to this coordinate system, I must have negative value of the displacement. But because we consider default direction, that's why I'm choosing the positive value for the displacement at point C. So automatically we must have minus, negative value after finish my calculation. Then can you calculate the strain? Yes, I can calculate this once because I have the displacement field. I can calculate the strain. Epsilon BC is, how do you calculate this? Because this is my coordinate system, UC minus UB divided by the length of BC segment. The UB is equal to 0. This is UC divided by the BC segment, the length of BC segment. Can you calculate the strain of this segment? Yes. The epsilon AC segment is equal to, now what is it? UA minus UC or UC minus UA. Because this is my coordinate system, UA minus UC, isn't it right? UA minus UC and the LAC. Then make sure that UA is already equal to 0 because of boundary condition. Kills the minus UC divided by LAC. Is it clear, right? And then what's the next step? So I just handle my displacement and strain. The next step is I need to handle the stress value. My stress sigma BC is equal to elastic modulus of BC segment and then strain of BC segment. But make sure when we calculate strain and displacement, I never talked about the modulus or the loading condition. Okay, this is purely related to motion and deformation. So only when we consider the material law, we consider the elastic modulus here. So this is equal to LBC, elastic modulus of BC, and then UC. Alright? And the sigma of AC segment is equal to elastic modulus of AC segment, the strain of AC segment. Yeah, everything is here, one by one. Okay? Do not consider, more than one equations at the same time. So we are talking about only one condition at the same time, UC. Isn't it right? This is calculation of stress, and this is calculation of strain. Now what's the next step? The next step is I want to check the force equilibrium for here. So if you look at this point, I have load P, and then this is my stress of AC segment, the stress of BC segment, BC. Okay, let's check the force equilibrium. Sigma AC of area of AC segment minus sigma BC, and then area of BC segment, the minus P is equal to 0. Okay, so AC is here, BC is here. So minus LAC EAC area of AC segment times UC, isn't it? And then minus BC is here, the LBC, elastic modulus of BC segment, and then the area of AC segment, BC segment, UC minus P is equal to 0. So I have one unknown and one equation. So UC is equal to minus of P divided by elastic modulus the area of AC segment plus BC, EBC, ABC. Okay, so we have minus sign automatically. Do you have any questions? Look, so once we have all these answers, then we can plot, look, so using UC, you can plot the actual displacement diagram. Then we may note that ADD, and then also we can plot the distribution of strain in this coordinate system, and then we can plot the stress value. By multiplying the cross-section area, we can obtain the internal force too. So we can draw the actual force diagram too. How? The actual force diagram is what? Sigma BC times area of AC. Then this is equal to NAC. NBC is sigma BC times area of BC segment. So everything is here. Look, BC and AC. Okay? Because we calculate UC, just plug in UC here. And then multiply cross-section area to the stress value. Any questions? Okay, so we have an example problem. Do you have any questions? Any questions? Okay, let's consider an example problem. So I have two bars, okay? Because of leveraging effect, the load applied to point E and then forms an external force into point B. So now let's pay attention to this bar. The question is, we have to calculate the vertical displacement at point C. That's the question. So how do you calculate the vertical displacement at point C? Vertical displacement at point C is what? First we have to choose our coordinate system. Let's consider this is positive direction X. Then my UC is what? The downward direction, isn't it, right? So UC may be calculated as, UA plus elongation of AB segment plus elongation of BC segment, isn't it? But because of boundary condition, UA is equal to 0. That's why we need to calculate elongation of AB segment and BC segment. How do you calculate elongation of AB segment? Elongation of AB segment, first we have to calculate the flexibility. So L1 divided by the elastic modulus of first segment and then cross section of first segment. And then we need to calculate the internal force. Make sure that the internal force, if the force stretches the member is positive and the compressed member is negative, alright? And the elongation of BC segment is similar to this, E2, A2, and then internal force of BC segment. Okay, so here L1, E1, A1, and L2, E2, A2, they are given a part of the solution. That's why we don't have to pay attention to that. So only information that we need is NAB and NBC. Okay? So I have a support, and then I have A1, and then I have what? So P1, and then I have force PB. So let's try to calculate PB. Okay, look, because this is my coordinate system, default positive, that's why I'm choosing PB downward. But let's consider the moment equilibrium with respect to point D. So I have P2 and then PB, and these are arm lengths. Arm lengths are A and B. And then PB is simply minus B over A P2, isn't it? So B times P2 should be equal to A times PB. Okay? So this is equal to minus B over A P2. Alright, so let's try to calculate the reaction here. My reaction R. Reaction is from the force equilibrium. Reaction R is what? Minus P1 minus PB. This is equal to B over A P2 minus P1. Okay? Now can you calculate these internal forces? Yes? You can calculate this, right? Please tell me you can. R, and then this is the direction of internal force N. Where is it? NAB. Okay? And then let's look at segment, the next segment. I have P1, I have NBC. Yeah, if you use the force equilibrium, you can calculate all this information automatically, isn't it? So let's consider another approach. So another approach is we want to consider first we want to consider all the forces. Let's say P1 and then PB. As we calculated just before, this is PB, right? We need to identify all the forces, and then I have reaction. And this is my coordinate system. So once I have a coordinate system, then I can plot my displacement field. So because this part is supported, then this is equal to 0. Point A is equal to 0. The displacement at that point is equal to 0. And then I may have non-zero displacement at point B, UB. And also I have another non-zero displacement at point C, C. Then this is my distribution of displacement. Then can you calculate the strain? Yes, I can calculate the strain. Strain distribution is, first part is what? UB minus UA divided by the length L1, isn't it? This is my strain. Okay? This height is equal to UB minus 0 divided by L1. Okay, this is my strain. Strain is constant. Look, strain is nothing but the slope. This is a linear distribution. That's why we have constant strain. And then also here I have another strain distribution. This is UC minus UB divided by the length L2. Is it clear? The next step, I need to calculate the stress distribution. stress distribution is strain times elastic modulus, isn't it? So E1 times UB divided by L1. And also here, constant. The E2 times L2 UC minus UB. Is it clear, right? Alright. Okay. And then what's the next step? The next step is I can calculate internal forces. Internal forces, to calculate internal force, we simply multiply the cross-section area. So E1, A1 divided by L1, UB. E2, A2, L2, UC minus UB. Isn't it? Then what's the next step? We need to check the force equilibrium. Here and here and here. Then we can determine all the information automatically. You understand? Any questions? Okay, today we discussed how to tackle statically indeterminate structures. So if you understand the three conditions governing the mechanical systems, actually there's no difference between the statically determinate structures and the statically indeterminate structures. Starting from the equilibrium condition, or starting from displacement compatibility conditions, if you consider each equation, each condition sequentially one by one, then you can solve your structural system without having any difficulty. Okay, so next time, we want to discuss the example problem today. Okay, let's consider example problem today. So first we have to idealize the problem. So we have steel cylinder, and then the steel cylinder is combined with the copper tube. Okay, so it's kind of parallel system. So I have a rigid plate, and the load is applied to this rigid plate P. And then I have a copper cylinder, and then inside the steel cylinder, copper cylinder. And it's supported by here. And its length is equal to L. Okay, first I wanna choose this coordinate system X. So this is my coordinate system X, and this is my displacement. And because this point is supported, this is equal to 0. And then let's say I want to call this point, say B. Okay, so let's consider point B. And then I must have here, I may have non-zero displacement UB. And this is my displacement distribution. And then let's try to check the strain distribution. Strain distribution is UB divided by the length L. This is strain distribution, isn't it, right? Now how about stress distribution? Now we have two different materials. Stress of copper and the stress of steel. And then we have to multiply elastic modulus of copper, EC, L, and UB. And then for the stress, for the steel, we need to multiply the elastic modulus of steel divided by length L and UB. Isn't it? Okay? Alright, so now I want to check the force equilibrium for a free body diagram. Let's consider free body diagram here. I have force P, and then I have copper part. So I have stress in the copper cross section, sigma copper. And then I have steel part. And then this is the stress of steel part. So let's check the force equilibrium. So P, if you consider downward direction default positive for this free body diagram, P plus sigma C and the area of the copper plus stress of steel, area of steel is positive, is equal to 0. Okay, let's plug in the information of I made a mistake, sorry about it. No, because we are calculating the slope. This is constant, sorry about it. And then stress is constant too, because we multiply modulus to constant strain. Sorry about it, okay? Please correct your lecture note. So we have to remove this. Yeah. Okay, sorry about it. And then let's plug in here P plus L, and then elastic modulus of copper, the area of copper, times UB, plus length, elastic modulus of steel, the area of steel, and UB should be equal to 0. That's why the nodal displacement at point B is equal to minus force P EC L plus the stiffness of steel. Okay, once you calculate the displacement, nodal displacement, then I can determine the stress of copper and the stress of steel. Once we have stress of copper and stress of steel, can you plot the actual forces too, right? The internal forces. And then this is the corresponding strain distribution, and this is the displacement distribution. So we can determine all the informations automatically. Okay? So next time we want to talk about the thermal effect. So let me introduce you what's thermal effect. So although in our textbooks we want to consider only the thermal effect, but I want to generalize the thermal effect to non-mechanical effect. Sorry, non-mechanical strain. Okay, so make sure that Hooke's law is for only for linear elastic material. Okay, which means stress development is proportional to mechanical strain. But in reality, the strain is the superposition of mechanical strain plus non-mechanical strain. In this non-mechanical strain, we may have thermal strain or the shrinkage strain. Yeah, there are many. Or strain caused by the misfit or the pre-strain. So we'll discuss this effect next time. So let me stop my lecture here. Do you have any questions today? Any questions? The light for online lecture is really burning my brain. Maybe I have to use sunscreens. Any questions? Alright, if you don't have questions, let me start my lecture here. Today we covered some more than one subject, isn't it, right? So we discussed how to use three conditions to solve or to tackle statically indeterminate structures. And once you understand this, the role of three conditions, there's no difference actually between the statically determinate structures and the statically indeterminate structures. Okay, so you may follow the procedure given in the textbook, or you can solve the problem using the three conditions one by one. You can do that, no problem. Okay, please check my lecture note carefully. If you have any questions, and please let me know. Or if you don't like talk with me, then you can talk with my TA for your discussion. Okay, so let me start my lecture here. See you next time.